to the next topic, which is still part of Chapter 12, and that's mass spectrometry. Okay? And do notice that that's not the same word, right? Mass spectrometry, not mass spectroscopy. They really are different, right? Spectroscopy, again, we've talked about this a few times. That's the interaction of the electromagnetic spectrum and matter. Mass spectrometry does not work that way. Okay? It's different. And how it's different is the instrument essentially breaks a molecule into its pieces and weighs the parts, and then reports to you what the parts weigh. That's pretty cool, right? But that's not shining a beam of light at it of some frequency and seeing what's absorbed and what's not absorbed. Okay? So it's a very different technique. As far as the information that comes out of it and what makes it useful to us is this has become the way to determine a molecular mass. It's really good at it. And there are two levels of precision with determining a mass. And there's high resolution mass spectrometry and there's low resolution. Low resolution is a lot less expensive and therefore a lot more common. High resolution is a very precise instrument and it can measure masses to about 8, 9, and sometimes even 10 decimal places. That's very precise when you think about it. And why have that level of precision? Because the exact masses of the various isotopes found in nature, if you have that precise a molecular weight, you can know exactly what the molecular formula is. With low resolution, you're only measuring 2 decimal places at best. And given only 2 decimal places, then there will often be a couple, perhaps even a few, maybe even several, depending on the particular situation, of molecular formulas that will have the same molecular weight to only 2 decimal places, but it's only one molecular formula that will have a precise mass that equals what the instrument gives you. So that's the main difference between high-res and low-res mass spectrometry. What else? Unlike the other techniques, mass spec does destroy the sample. As I said, it really does blow the molecule apart and weighs the parts. So you can't recover it. With an IR, you guys have done IR. You've put a sample onto the instrument. You can recover that sample if you needed to. If that's all you had in the world, you would do that, right? You guys make buckets of material in organic labs, so it's not crucial to recover the sample that went on to the IR, but you can. Likewise, NMR and UV vis, you can do the same thing there. The sample goes into the instrument and it comes out of the instrument without being destroyed. Mass spec's different. Fortunately, as it says, very, very small amounts are needed to run a mass spec on a sample. It says micrograms to picograms. That's not much, really. Okay? And that's pretty much it for that, right? Here's a graphic that shows you what the mass spec instrument looks like. This is really based on some of the initial mass spec instruments that were built back in the day. But it's essentially the same principles that are still used, right? One thing is this whole system will be under an extremely high vacuum. We're talking the kind of vacuum that the space shuttle experiences in near-Earth orbit where it is. Not when it's in Florida or Texas, but when it's up 200 miles above the surface. That's the kind of vacuum that's in here. So a sample's introduced, there's a gas that drives it through the instrument. It hits an electron gun, about a 70 electron volts bombards the compound that ionizes it. Why? Because it knocks one of the electrons of the molecule out of orbit permanently. So it ionizes the molecule, these rates accelerate it, And once the molecule has a charge, it can be deflected by a magnetic field. That's what's happening here. These two disks are labeled magnet. So it hits the magnetic field, and the magnetic field causes a deflection in the trajectory of the ions. And that's based on the strength of the magnetic field and the momentum that the has, right? More momentum means deflected less. Less momentum means it's deflected more. Now, given that they all develop a single positive charge, the thing that changes the amount of momentum is not the charge. It's the mass of the ion. So heavier ions end up being deflected less, and so they're outside, so to speak, of the beam. The lighter ones get deflected more. They end up inside of the beam. And then there's a detector. And the detector literally counts the ions that hit it. Okay? That's pretty neat. Okay, questions or anything? All right. Some of this has already been mentioned, but here it is written down so you guys can have it permanently. One reason for being under such a high vacuum is because the sample that's introduced into the instrument has to be vaporized. While the sample can be introduced as a solid or a liquid, though most instruments you have to dissolve it in a solvent and then introduce it to the instrument, the sample has to be vaporized. And that's accomplished two ways. One, the really high vacuum, and two, the injection port is usually at about 200 degrees C, and that will vaporize just about anything. And it has to be kept under that extremely high vacuum because there's something that needs to be avoided. And that is that once the molecule's been ionized, it has to be kept away from other molecules. And the way to accomplish that is by a very high vacuum, so that the probability of two molecules bumping into each other after ionization is remote. So you end up with unimolecular processes happening in the mass spectrometer. As I mentioned, there's an electron beam. It's roughly 70 electron volts. That's enough to knock an electron out of orbit of just about anything that gets hit. Right? See, it easily exceeds that of chemical bonds. And what's left then, as shown in the graphic here, the equation, right, that's just a very simple event that would happen in a mass spec. This, of course, is methane. You guys all recognize methane. I've shown the electrons individually that are involved in the bonds. Along comes the electron from the electron beam. It hits one of the bonding electrons and knocks it out of orbit for good. And it really doesn't matter which one of the 8 electrons I choose in this graphic to have knocked out of orbit. They're all equivalent to start with. So notice that the bond here at the 3 o'clock position has just one electron now holding the hydrogen fast to the carbon, because the other electron's been knocked out of orbit for good. It's gone. That makes this product of the ionization event a radical cation, right? Says that here in the last bullet, but I want you to realize why, right? Losing an electron, of course, makes it a positive charge. But losing an electron from a pair of electrons leaves a radical also, right? That's 2 strikes of instability against the molecule. And so it's a very unstable thing now. It's a very unstable molecule, and will likely go on and do other things. And so this is all shown so you get the point that 1 electron's lost, and there are 8 electrons that could have been lost. Any one of them could have been lost, and one of them was. But we usually don't bother showing all that. We just show this. So CH4 plus dot, to get the point across that now it's methane as a radical cation. Okay? Thoughts or comments?